Hi all, welcome back. And in this video, we are going to learn about virtual memory. Till now, we have seen about all the memory allocation techniques, whether it is continuous or non-continuous, and so now we will be talking about virtual memory in detail. So how is this virtual memory? So basically, virtual memories give an illusion. Okay, virtual memory gives an illusions to the programmer that a programs of large size, which is larger than the actual physical memory, can be executed. So basically, virtual memories gives illusions illusions to the programmer that programs are of bigger size, programs of larger size, larger than the actual physical memory, programs of larger size, larger than the actual physical memory can be executed. Okay, so this is about uh, virtual memory, but what it does means. Okay, so basically virtual and how does it gets implemented, so we will see about it in this. But first of all, learn this point that it gives an illusion to the programmer. So the programmer feels that even though program has a size which is greater than the actual physical memory size, then also it can be executed. Now how it is implemented, how it is possible that program of size larger than actual physical memory can be executed with the help of virtual memory. So basically, is implemented virtual memory is implemented using something called demand paging. Okay, virtual memory is implemented using something called demand paging, or we already have learned about segmentation, so demand segmentation. So we'll see what is demand paging and what is demand segmentation. So with this diagram that I'm drawing through, so how does but what is does demand paging means? So demand paging means loading the pages on demand. Okay, so demand paging means loading the pages into memory, loading the pages into memory on demand. That is whenever page fault occurs. That is whenever page fault occurs is called demand paging. Okay, now what is page fault and how we are loading the memory, loading the pages into memory? So let's say we already have seen this diagram. We have a processor which generates nothing but the logical address. So let's say the processor has generated a logical address of 13 bit. Before that, let me start with the memory. So this is our LAS, that is our virtual memory. We have been talking a lot about this, where our programs being stored. So this is our LAS, and this is our PAS. Now this PAS is nothing but the physical address space, and this is a logical address space. And let's say we have a physical address space of 4 kW. So logic whenever our program with something called 5 kW or 7 kW comes, so seeing this, we say that okay, we can't execute our entire program from here. But this logical address space gives us illusion that we have a space of 8 kilowatt and we can execute our program from here. So let's say it is divided into equal size pages. I mean, paging is implemented on that, and let's say each page size is having 1 kilowatt and so on. So all together 0, 1, 2, 3, 4, 5, 6, 7. All together we have 8 pages. And let's say for executing this program into the memory, we have, and here also we have made a division of 1 kilowatt pages, right? So this is nothing called frames. And then here we are bringing some of the pages required for execution from virtual memory to physical memory. Okay, so let's say shouldn't be so let's say what pages we are bringing. So here we are bringing some of the pages, like let's say we are bringing P7 at the zeroth location. Then we are bringing P4, P5 at the first location, P3 at the second location, and P1 at the third location. Okay, so although we have all these pages here, so we are bringing at certain points some of the pages into the main memory required for execution. So this is the current scenario. Let's say that the CPU addresses some pages. Let's say it addresses some pages with 13 bits, where P denotes the page number and D denotes the page offset. So this is 3-bit, this is 10-bit. Okay, and now we for implementing the paging, we have this page table to map the logical address generated by the CPU to the physical address. So this page table contains all the page number and their corresponding frame number. Okay, so for every page in the LAS, we have the corresponding frame number here in this page table. Okay, so all these are page number page number of the LAS. And for each of the page number, where is this page located in the physical access memory, address memory? Here we are mentioning. So zeroth page is located at nothing, no position. I mean, it is not present. First page is present at, I think first page is present at third. So it is present at third. Second page is present at it is not present. Third page is present at second location. Fourth page is not present in main memory. Fifth page is present at first location, and then seventh page is present at zeroth location. So this way we map the pages with the corresponding address in which they are present in the physical access memory with the help of page table. Right, now let's say the CPU generated something, an address. And yeah, whenever it generates a logical address, we see what page number is required by the CPU, and correspondingly we get from here the frame number from the entry. And from the frame number we just map it to F and D, that is the physical address. Okay, so here we get the frame number from here, and D is nothing but the page offset, which is same as the frame offset. Right, and from here we just refer to this memory. Right, it became so much, right? So this was the actual process. But now let's say what is called demand paging we were learning, right? So the very first, let's say the CPU generates something, a page request of 100. Let's say it wants to access fourth page. Okay, now it will start coming in for this. So the first request will be sent to the page table. So it will see whether in fourth page here, is it an entry related to the frame number present. So we see that okay, no, the page is not present in the main memory. Now what will happen when the page is not present in the main memory? Then it is a case of page fault. Okay, because the page is absent in the main memory. So now it needs to have this page into the main memory, and this will be notified to OS. So from here, let's say if it is not present, it will lead to page fault. And in the second step, what will happen? It will be notified to OS that there is a page fault. So OS will do, it will go to the, so in the second step, OS will go to the logical address space, and here it will try to find out whether it is second page, fourth page. Where it is fourth page, this one. So it will try to find out the fourth page, and it will try to bring that fourth page, this part, into the main memory. Okay, So it will try to bring this fourth page into the main memory. And now from here, the concept of demand paging start. So in the second page, it has in the second step, some OS an advice has been issued to OS that bring the fourth page because it is not present in the main memory. So bring the fourth page from the logical address space to physical address space. So here what happens, that in the third step, in the third step, it will go back and fetch this page. So it is fetching this page in third step. Okay, and then it is trying to bring this particular page into the PAS. But now here it sees that all the pages have been filled. So now it applies something called page replacement algorithm. Page replacement algorithm, we will, just a second. Okay, so it applies something called page replacement algorithm, and based on that it will replace certain pages that is present in the main memory. So let's say it applies some of the algorithm in which it replaces this page and instead it fills it with P4. Okay, so in the fourth step, P4 is now present in the main memory. Now P4 has been produced in the main memory. So what will happen for P4, whenever one page is produced into the main memory for P4, again in the step number 5, entry will be made into the page table. So corresponding to the page 4, we will be having entry like 01, and this entry will be cancelled. Right, now we have got this entry. Now the CPU got this part, is initiated of this part. Now what will happen, it will fetch this page back to, from here it will fetch this page, and it will get to the corresponding it will execute the corresponding instruction based on the word offset. Okay, so it basically, the thing that I want to show here is when the page is not present in the in memory, then it is notified to the CPU, notified to the OS that it is a case of page fault. The CPU, the OS will take an action based upon how to bring that page from the LAS to PAS, and correspondingly how to update the entry in the page table. So this is how demand paging is introduced in case of OS. So we'll see it step by step, whatever I have illustrated. So first of all, in step 1, what happens, in step 1, CPU is trying to execute a page. CPU is trying to execute a page in the main memory, but seeing from the page table, the page is currently not available in the PAS. Okay, the page is not available in the PAS, resulting into page fault. Okay, now in step 2, the OS is notified that there is a case of page fault. So program execution will be stopped. Program execution will be stopped, and a signal will be sent to OS, and a signal will be sent to OS regarding the page fault. Okay, so the OS is getting notified regarding the page fault. Now, what will the OS look for? The OS will look for the specific page in the logical address space. So OS will search for the required page. OS will search for the required page in the LAS, I mean the logical address space, and on being found, OS will try to bring that page into the main memory in step number 4. So the required page will be brought from the LAS will be brought from the LAS to PAS. Okay, so required page will be brought from LAS to PAS. Now in step number 5, here only while bringing the page, some page replacement algorithm that we are going to see next, some page replacement algorithm is used for decision making as to which page needs to be replaced. So some page replacement algorithm is used for the decision making for selecting the page for replacement. Okay, for selecting the page for replacement. So some page replacement algorithm will be used for the purpose of decision making here, right? And in step number 5, the page is updated and respective page table entry will be updated accordingly. The page is replaced and the corresponding PTE page table entry is also updated, and the correspondingly PTE is also updated. Okay, so this is step number 5. And then in step number 6, the OS will notify the CPU that the page has been correctly be replaced and it needs to start the program execution. So signal will be sent to CPU to continue for the program execution. To continue for the program execution. And CPU will access the required page, and CPU will access the required page in the main memory to continue program execution. So these are the basic steps for demand paging, right? We'll see once again how does this happens so as to revisit this part. Before that, I would like to tell you about something about page fault that we talked about here. So page fault occurs in step number 2, where the CPU is trying to access a page and it is not found into the main memory. So here CPU program execution gets stopped and OS is notified regarding the page fault. So this page fault is a common scenario in case of demand paging. So basically it happens when CPU is trying to access a page assuming that it is present in the main memory, but it is not present. So OS is notified regarding this and OS is trying to search for that page in the LAS and then trying to bring that required page from LAS to PAS, right? And then applying page replacement algorithm, and then after replacing that, the corresponding PTE is updated and OS is notified to begin that execution. Okay, so so page fault, whenever it occurs, it requires some service time because CPU needs to go to the LAS to search for that page, and then applying the page replacement algorithm to replace that page from main memory to bring to make space for the new page, and then updating the PTE. All this requires a service time. So basically it is the time taken to service a page fault. To service a page fault, and it includes time to perform time to perform all the six steps. It includes time to perform all the six steps. Okay, so basically if page fault time is s, page fault service time, page fault service time is equal to s, and main memory access time is m, and let's the page fault ratio or page fault rate is p. Okay, so page fault rate is p. Then if we need to calculate the effective memory access time, then it is p time. Let's say page fault has occurred, so accessing the main memory plus servicing time plus 1 minus p into accessing the main memory time, because here the page fault has not occurred. Okay, now here this M will be included in S only, because uh, it is entirely the six steps. So this S includes the main memory access time as well, includes the main memory access time as well. Okay, this is one thing to note. So this servicing time includes all the six above six steps. So in the last step, we are accessing the main memory to continue the program execution. So it includes all the basic six steps that we just talked about. So let's go and revisit this once more. And then we will be solving certain questions based on that, and then we will learn about the different page replacement algorithm. Basically there are four algorithms, so that we are going to talk about next. Okay, so let's revisit that part again. So we have one logical address space. So this is our logical address space of 8 kiloword, and it is divided into 1 kilowatt pages, and each page is having particular address 000 001 100, sorry, 010 100 101 110. What is this? I just mixed something. Okay, so this is 010 011 100 101 110 and 111, and each page is having size of 1 kilowatt. So this is our not PAS, this is our LAS, and then we have the PAS, in which we are bringing some of the pages from the virtual memory at a time. So it is 4 kilowords, and it is a PAS, and 0001 1011, and here we are having all the pages like P7, P5, P3, and P1. And this is how the when the CPU generates our logical address. So processor is generating a logical address which consists of the page number and the page offset, and here it wants to access the page number 4 with certain page offset. So this is issued to the page table. Now page table contains the entry for every page in the LAS. So it will go back to here and try to seek for which page, fourth page, right? 010 011 100 101 110, and one more, I think, 111. Now for each page there is a corresponding frame number. So for 000, no frame number. For 01 page, we have it is present in the third frame, right? So it is third. For second we don't have entry. For third we have 10. For fourth we don't have entry. For fifth we have 01, and for seventh we have 00. So it tries to look for the page number 4. So it supposes that it is not present in the main memory. So then what happens? So in the first step, CPU tries to find out the page, fourth page, but it seems that it is not present in the main memory. So OS call is being made that to bring that page from the main memory, from the virtual memory to the main memory. So the OS starts processing. So from here in step number second, OS goes to the virtual memory, right, to fetch this page, fourth page. Now it tries to get onto this fourth page to here. So in step number 3, it fetches this page into the main memory, right? So what does the step number 3 includes? In step number 3, OS will search for the required page in LAS. So in step number 3, OS searches for this page in the LAS. So now in step number 4, it applies page replacement algorithm to replace some page if space is not there, and then accumulate the fourth page here somewhere and tries to update the entry here. So it updates the entry to 01 and it cancels this entry, right? So now page in step number 4, this page is made available. Then in step number 5, it issues command to OS, a signal to OS that yes, the page has been replaced. And then in step number 6, what happens that the CPU then tries to look for this page, fourth page. It finds the corresponding frame number, then it makes a physical address, right? F and D, 01, and D is the same as here, and then it goes to the main memory and then it fetches the page. So in step number 6, the OS does the memory access. So this service time, page fault service time, includes all these steps from step 1 to step 6, right? So if page fault ratio is P, then EMAT is equal to P into S plus 1 minus P into M, because here just the main memory access time is required. Okay, this way. So this is all about demand paging, and please note that the page fault service time is larger than the main memory access time. Okay, so this is one important thing. So just solve one question and we are good to close this particular video. So let's say we have something called a system with let's say we have the main memory access time MMAT is given as 35 nanosecond, and page fault service time, that is S, is given as 175 nanosecond, and page hit ratio is 75%. Then EMAT is asked. So if page hit ratio is 75%, that is 75 upon 100, that is 3 by 4. Okay, so page hit ratio is 3 by 4. So if there is a page hit, then we just need to access the main memory. If there is a miss, 1 upon 4, then we need to do the page service time, right? So this way, so we will just add it up. 1 upon 4, 3 into 35 plus 175, and that is equal to 1 upon 4, 105 plus 175, and it is equal to 10, 8, 280 upon 4. So I think it is equal to 70. Okay, so overall EMAT is 70. So this way we can solve. Here important point to note is S is thus includes the main memory access time. Okay, when there is a page fault, then it will include all the basic 6 steps, right? Like this way we can have more questions also, but the basic idea remains the same. The EMAT formula we need to remember is effective main memory access time is P into S plus 1 minus P into M. Please note that P is the page fault ratio, S is the service time, including step number 1 to 5, 1 to 6, okay, not 5, 1 to 6. And 1 minus P is the page hit ratio, and M is the access time. Okay, this is an important formula for every such questions. So in the next video, we are going to see about some of the page replacement algorithms, which is very important, and which is mostly asked how this OS replaces the page or in the demand paging method. So this is all about virtual memory demand paging and also I hope I'm able to explain some of the key points. If you do have any doubt, questions, or comment, please do post in the comment section. Thank you very much for watching.